Hi. We didn't finish the applications in class for section 4.4, so I wanted to make you a video for those. And let's get started. Number 58 says change f of x equals 50 times 9/8 to the x to an exponential function with base e and approximate the growth rate of f. Now this is an exponential function, but it's base 9/8. And the instructions are asking us to write it as base e. Well, hocus pocus, how do we change 9/8 to an e? Well, sometimes what we have to do in calculus is try something, write down something, see if we can write an equivalent expression to this that's base e. And if we get it wrong, we erase it and try something else. I don't think it's going to affect that coefficient of 50, but I just have to write 9/8 as e to the something. E to the something. What would that something have to be so that e to the something would undo each other and just leave me 9/8? Well, I know what undoes e to the something. Natural log does. If I wrote that as e to the natural log of 9/8, would those just undo each other and leave me 9/8? Sure they would. And if so, if I raise that to the x power, just like this 9/8 is to the x power, I do have an equivalent expression. These just undo each other and leave me 9/8. So I have an exponential function with base e now, but approximate the growth rate of f. Well, think about the continuous compound interest formula that we learned in the previous section. A equals P times e to the RT, where R is your interest rate and T has to be your time in years. And I told you really that formula doesn't only apply to continuously compounded interest. It applies to anything that has exponential growth or exponential decay. So if we rewrote this with different letters, it would look more like what you would see in a biology book probably. Instead of having a P, a biology book would probably have A sub 0 for the initial amount. And they use a K for the growth or decay rate, whereas this formula used R for interest rate. And the biology book might use X for your period of time, where compound interest formula used T. The only difference is in the continuously compounded growth or decay formula, X doesn't have to be in years, it can be in any units. So what we're looking for is this value of K, this growth or decay rate, and it has to be the coefficient of X when this is written in exponential form with base e. So I'm thinking this is e to a power to a power. When I raise an exponent to an exponent, what do I do with them? I multiply them. E to the natural log of 9/8 to the x is the same thing as e to the x times natural log of 9/8. Because when you raise a power to a power, you multiply. Now that natural log of 9/8 is what's multiplied times x in the exponent. That's my growth or decay rate. So I just need to enter that. Well, if I want to leave an exact answer, it's natural log of 9/8. If I want to punch it on the calculator and get a decimal approximation, I've already done that just to save time. And I'm going to tell you that natural log of 9/8 is 0.1178. That's the coefficient of my x. So that is my growth rate. Because it's positive, it's a growth rate. If that coefficient was negative, it would be a decay rate. And if you want to write that as a percentage, because that would kind of make sense for a growth rate, we could write that as 11.78%. And it would be per whatever the units are on time here, but we don't have that given to us. So we just have to say 11.78% is the growth rate. We don't know if it's per day, per week, per hour. We weren't given that information. So we changed base 9/8 to base E, and then we calculated the coefficient of X, and that was our growth rate. Number 60 is the same thing, except for we can expect that exponent to be negative because this is a decay rate. We would say f of X is 100 e to the something, and I want the e to the something to undo each other and just leave us a half. So e to the natural log of a half. That e and that natural log undo each other and just leave us the 1/2. So as long as I keep up with the exponent outside the parentheses, that's equivalent to the line above it. And then as we did here, we could say when you raise a power to a power, you multiply them. So this exponent becomes x to the natural log of 1/2. I'm going to write it as x to the natural log of 0.5, just because that's easier to punch on the calculator. And if I get a decimal approximation of natural log of 0.5, that'll be my growth rate. Actually, my exact growth rate is natural log of 0.5. A decimal approximation of my growth rate would be, let's see, I've already punched this on my I left out my e right here, I'm sorry. E to the x times natural log of 0.5. Natural log of 0.5 is negative 0.6931. So this is 100 e to the negative 0.6931 x, where that coefficient of x is my decay rate. Now, actually, if you ask me for a decay rate, I probably wouldn't say the decay rate is negative because the word decay already took care of the negative. I would just say the decay rate is 69.31% per whatever the units of time are for this problem. All right, those are pretty much the same. Let's see what 62 is. The radioactive bismuth isotope disintegrates according to this formula, where K is a constant and T is the time in days. Express T in terms of Q and K. That just means solve this equation for T. Well, when we get the T by itself, first, I need to get this exponential expression by itself. And I can do that just by dividing both sides by K. Q over K is 2 to the negative. You know what? My eyes could interpret that better if I wrote it as 1/5 T. Are those two things the same? T over 5 and negative 1/5 T? They are. So how do I unexponentiate that negative 1/5 T? How do I get it down out of the air? Well, I know what undoes 2 to a power. Log base 2 undoes 2 to a power. Log base 2 is something I can apply to both sides. And then on the right-hand side, say log base 2 of 2 to a power, undo each other and just leave you the power. So I have -1/5 t equals log base 2 of q over k. What's the only thing I have to do to have the t by itself? Multiply both sides by -5. I'll have t is -5 times log base 2 of q over k. With the exponential expression by itself, take log base that of both sides to undo the exponential expression on the right, and then finish solving for t. All right. Number 65 says use the Richter scale formula R equals log, and without a written base, that's log base 10 of I over I sub 0 to find the magnitude of an earthquake that has an intensity of 100 times that of I sub 0. Well, let's talk about earthquakes a minute. A seismologist, an earthquake scientist, takes a seismograph to the site of an earthquake or a certain distance from the site of the epicenter of the earthquake and measures the rumbling of the ground. The rumbling of the rocks in your driveway on a normal day, it's called the little bitty almost nothing earthquake. That's what I call it. Scientists call it zero level earthquake. Zero level earthquake is what your gravel are doing in your driveway on a normal day. All other earthquakes are written as some multiple of that. So the intensity of this earthquake is 100 times that of the little bitty almost nothing earthquake. So we want to find the Richter scale rating when the seismograph measures rumbling 100 times that of a normal day. Well, here's the Richter scale formula. R equals log of the intensity of this earthquake is 100 times IO divided by IO, because that's what the formula says. The IOs divide to give you 0. R is just log of 100. And since this log means log base 10, what's the exponent of 10 that gives you 100? It's 2. An earthquake with Richter scale rating of 2 is rumbling 100 times what's going on in your driveway on a normal day. A Richter scale rating of 3 is rumbling 1,000 times what goes on in your driveway on a normal day. So you can see how devastating a Richter scale rating of 8, an earthquake of Richter scale rating 8 would be. That's 10 to the 8th times what's going on in your driveway in a normal day. All right, number 68. The formula for the decibel rating of sound looks a lot like the formula for the Richter scale rating of an earthquake. With earthquakes, I sub 0's the little bitty almost nothing earthquake or the 0 level earthquake. With the decibel scale formula, I sub 0 is the lowest sound that a human can hear, the little bitty almost nothing sound. So the Richter scale, not Richter, the decibel scale formula, I'm not sure why alpha is used for decibels, but the formula is 10 times the log of the intensity of sound divided by the intensity of the little bitty almost nothing sound. A sound intensity of 140 decibels, that's what A is, produces pain in the average ear. Approximately approximately how many times greater than the threshold of sound does the intensity have to be in order for alpha to reach that painful level of 140 decibels? That's just saying put 140 in place of alpha and solve for I. No. If we're solving this logarithmic equation, first I need to get the the logarithmic expression by itself. I'm going to divide both sides by 10. 14 equals log of I over I sub 0. And then how do I unlog base 10 something? Well, I can write it in exponential form. The base is 10, so in exponential form, this would be 10 to the 14th equals I over I sub 0. I'm just going to write change to exponential form here for you. 10 to the 14th equals I over I sub 0. I'm solving for I, so I is 10 to the 14th times the threshold of sound. 10 to the 14th is a 1 with 14 zeros on it. That's the intensity, or that's the number of times the little bitty almost nothing sound that will be painful to the average human ear. The answer is just 10 to the 14th times the threshold of hearing. Okie doke, 2 more. Number 70 says the population N of T in millions of India T years after 1985 may be approximated by the formula this. And notice this formula looks a lot like this formula with different letters in it. The coefficient of E is your original number. The population of India in 1985 was 766 million. The question is, when will the population reach 1.5 billion? Well, I don't want to keep up with all of those zeros in 1.5 billion. I just want to know how many millions 1.5 billion is, and then I'll keep up with the word million in my answer. Let's see, 1.5 billion is 1,500,000,000. And if you want to know how many millions that is, just divide that by a million. Or cover up 6 of the zeros. 1.5 billion is 1,500 millions. So since 766 is in millions, I'm going to have to write this 1.5 billion in millions. The question then is, when is N of T 1,500? Well, put 1,500 in the place of N of T. And solve that for T. We have to divide both sides by 766. And then to solve this logarithmic equation, we changed it to exponential form. To solve this exponential equation, we could change it to logarithmic form. And since it's base E, we'll say natural log form. In logarithmic form, this would be natural log of 1,500 divided by 766 equals, remember it's always the exponent that's on the side by itself. You can double check that by changing it back to exponential form. In exponential form, it would be e to the 0.0182t equals 1,500 over 766. Now, just to save time, I've already punched this on the calculator. And we've got run out of space here, but I punched t equals natural log of 1,500 over 766 divided by 0.0182. And I'll let you punch. You can pause to punch that on the calculator. Make sure you understand how to punch it on the calculator. And if you don't, send me an email. But I got that to be darn close to 36.9. Since the question is, when will the population be 1.5 billion? That's going to be about 37 years after our original time was 1985. 37 years after 1985 is actually next year. It's 2022. Since this is a little bit less than 37, we're going to say sometime near the end of 2021, the population of India will be 1.5 billion. Google that now, and it's pretty close to 1.5 billion. All right, last one. If interest is compounded continuously at a rate of 4% per year, approximate the number of years it will take an initial deposit of 6,000 to grow to 25,000. That's a perfect time to use our continuously compounded interest formula. That's compounded continuously. Our initial deposit is 6,000. That's my P. 25,000 is what I want to have at some point in the future. So 25,000 equals 6,000. E to the 4% per year is 0.04. T is what I'm solving for. So divide both sides by 6,000. I could reduce both numerator and denominator by 1,000 and just have 25/6 equals e to the 0.04t. And just like I did on number 70, change it to logarithmic form. In logarithmic form, that would be natural log of 25/6 equals 0.04t. Change it back to exponential just to be sure. E to the 0.04t equals 25/6. And then divide both sides by 0.04. Notice I don't pick up my calculator until I have that t by itself. 25/6 is not a terminating decimal. So if I use a decimal approximation here and then do some other stuff, I'm going to compound my error. Keep it exact until you get the t by itself. You can punch that on the calculator and you'll get darn close to 35.7 years. All right. You should be able to do these applications at the end of 4.4. If you have any questions, email me, and please, please, please send me a picture of your work so I can see how far you got before you got stuck. All right. Have a great day.